Good morning and welcome back. Up to today, we have discussed several conditions. We discussed electric field and magnetic field observed at far wrong, that at point of observations. And we know electric fields come from two parts. One is the velocity field, the other is acceleration field. And in section 14 point, let me change the index. Section 14.1, we discuss the velocity field. And velocity field, the idea of the velocity field is related to chapter 11, special relativity. You can use velocity field, or you can consider special relativity, Lorentz transformation. The result will be the same. And last time, 14.2, we talked about acceleration field. Okay, we consider these terms. We use spatial techniques. We obtain the Lamar's formulas at very low speed and generalize the Lamar's formula to more to relativistic case. And we rewrite the total power radiated into three forms, and we consider acceleration parallel to the observer, uh, three conditions, actually two conditions, two examples. But remember, we always consider here what happened to here. What's the difference? That's E field and B field at point of observation. And how about here? E field and B field at point of radiations. Okay, that's angular distribution of radiation emitted by an accelerated charge. This observed here and observed here will be different because observer here is fixed, and observer here, particle radiated here is travel at a very high speed, for example. So there will be a time, uh, the time here at t prime and t will be different. Okay. Therefore, we need to consider special relativity. Okay. So the conservation of power, then we should do something. So today we want to know the angular distribution of radiation emitted by an accelerated charge. Pointing vector comes from here. That is from observer's positions, observer's point. And E is here, B is here, and they are related to T prime. T prime is from here to here. Okay? Oh, sorry, N is the direction of propagation. S dot N is equals to C over 4 pi E squared. So eventually, neglect the velocity field. We neglect these terms. We just consider this term is here. It's evaluated at the retarded time. Okay? Today we will cover only 7 pages, not too much. In this section, we are interested in the angular distribution of the power radiated by the charge. So X here is here, gives the power per unit area received at the observation point. Power radiated by the charge into the unit solid angle, the P here, the omega is in general different from the power received over the area subtended the study angle. Power emitted at here and power received at here will be different. Okay, the reason is that motion of the charge toward or away. Just imagine if the particle moves toward the observer, it will shorten the radiated pulse. If the particle do not move, then there will nothing change. But if the particle move in the same direction as the wave propagate, the pulse will shorten. And so the result in increased power at the observation points because of total energy received must equal to the total energy radiated, conservation of energy. So emitted from here and received here will depends on the velocity and depends on the direction of V and N. Okay? You can imagine. If we emit in the same direction as N, energy will be increased. However, if the particle move away from the reason is that the particle toward or away from the observation point, then the energy will be decreased. Okay, to just too extreme. We should right now we just write here, but now we want to express here. Okay, last to express the power radiated in terms of power received. Power radiated in terms of power received. Power received we already know and know very well, but we want to know power radiated from here. Okay, we need to determine the ratio of dt to dt prime. That's the received pulse length and radiated pulse length. They will be different. Okay, how to do that? We know T and T prime are related. Okay, the observation time T and retarded time or radiation time T prime are related through these equations. So dt over dt prime is 1 plus 1 over c dr t prime dt prime. And that's v t prime dot n t prime. And v t prime over c is minus beta t prime dot n t prime. A pulse of duration dt received at here at x and t is radiated by the charge at here at this point for a duration dt prime equals to dt minus this one. Note that. So dt and dt prime are quantity in the same reference frame. Okay, so you can write r squared, that's pointing vector in the direction of n prime, into this one. Okay, that's in left frame, and this is r squared times dt. Once again, be careful. We have these terms. Okay, in the same left frame. In terms of this one, we need to change this one. Okay, that's why we want to study the p at t prime. That's the major difference here. The p, okay, let's observe. So we change to here at emitter. Okay, so in both the p t prime over the omega and the pt over the omega. The omega is with respect to the charge. Okay, good. I hope you got some ideas. We know this one, but now we want to calculate this one. The notation, the t and the t prime is related here. We just change the t, so we change to here. And now we find the relation between the t and the t prime, that is this one. So this terms can be changed to the uh, uh, observer emitter. Okay. Therefore, dp d tau is equal here. So r squared we write. So that's the major difference. Extra terms. Let's extra terms here. And this term is here. This term is here. Or this term is here. So eventually we got the t prime. We have these terms. Okay. What happened? One, remember, cubed in the denominator, and we have square, so we have to the 6. That's a correction here. Actually, we just correct these terms. Okay, we just correct to the 6. Now we change to the 5th. Okay, you can imagine people initially consider it should be to the 6th, but later on they found it's not that critical. It's very important because we need to correct these terms. And let's change a lot. Where n beta dot are to be evaluated at the retarded time t prime gives the power radiated into the unit solid angle in direction of n in terms of the charge E and instantaneous beta and beta dot of the particle. Okay, so next one, I will give you two examples. Case 1, beta is parallel to beta dot. Okay, that is the acceleration is the same as the velocity. Therefore, we got this one, the pt prime over the omega, e squared, and beta is the same as beta dot. Okay, beta is the same as beta dot. So beta cross beta dot is 0. Therefore, n, not therefore, we can simplify this one. N cross beta dot equals beta dot square sine square theta. Okay, so in terms of capital theta, we can reduce to theta. What do I mean? Remember, in this case, we use n and beta dot, and the angle is capital theta. But now we change to lowercase theta. Okay, because it's not just we align beta and the beta dot. We use this one, n v, so their angle is theta. Their angle is theta. Yeah, okay. Their angle is theta, okay? So we can write into this form. Therefore, the pt prime d omega equals to e squared, that is v dot square sine square theta. And here we just have beta cosine theta to the 5th. Okay, so we can integrate the solid angle. So give us 2 pi. After integration, we got this one. You can check by yourself. That will agree with 14.26 and 14.26. ED200611. For beta smaller than 1, these equations reduce to Lamar's formula with the radiation peak at 90 degree, okay, perpendicular degree. When beta is very close to 0, it just focus on perpendicular angle, and not this one. More an increase in the magnitude with the maximum intensity at this one. Okay, let's simplify to when beta is very small, we can reduce to Larmor radius. However, beta is very close to 1. Angular distribution is tipped forward more and more, just like a cone. Uh, Not a cone, but a shell. More and more in magnitude with the maximum intensity at here. The maximum intensity theta can be found from here. Let's beta parallel to beta dot. Let's beta dot is in the same direction. What happens if beta dot is perpendicular to beta? Not finished yet. Another case. Beta close to 1, we have theta is smaller than 1 because the radiation will be focused, will be tipped more and more. 1 minus beta cosine theta equals 1 minus beta 1 minus 1 over 2 theta squared because theta is very close to 1. Okay, so 1 minus beta squared 2, so we can rewrite this one. Beta very close to 1. Okay, beta squared 2 beta. So this part can be simplified to here. Not much difference because beta very close to 1 and theta very small. Theta very small. So this one equals to 1 minus beta squared over 2. Not much difference. And beta very close to 1. 1 theta squared over 2. And by this way, we can rewrite into 1 over 2 gamma squared, 1 plus gamma squared theta squared. Okay, so these terms, these terms can be rewrite into this form. And these terms, theta squared, we can rewrite into this form. Okay, we just try to simplify the expression. So the p t prime d omega, when beta is very close to 1, it just looks like this one. The distribution is here. So from this one, we can calculate the angle maximum intensity is 1 over 2 gamma. Theta square averaged 1 over that the Riemann square angle will be equals to 1 over gamma. Okay. So this page is quite not very difficult, but will help you understand what's going on. It gives us a distribution of the radiation at the charge's viewpoint. At the charge's viewpoint, okay? Okay, so Riemann square. Move on to next one. Okay, this one is not good if observer is here. It's good or not good, it's hard to say. If you are here, if you are here, then this one is good, but it lost a lot of energy because as mutual symmetry, only a small fraction of the energy will move to here. So that's not efficient. And actually, we know if beta and beta dot are parallel, the radiation is not that much. Okay, actually, don't worry at all. Go back to here. Here, that's linear accelerators. That one is very small. Don't worry too much. That means the P and acceleration force is parallel. The radiation is not too much. Even though the gamma is very large, the radiation is still not too much. Don't worry too much. Okay. Therefore, we will focus on case 2. Case 2, that means the P, that means beta is perpendicular to beta dot. We will use this one. Let's use this one again. And remember, we have a correction. Okay, so a particle is moved here, and particle move in a z direction, but change beta dot is in the x direction, x, y, z. Observer is here, is n. Okay, in terms of uh, r, theta, phi. So beta parallel to the z directions, beta dot parallel to the x directions. N in terms of sine theta, cosine phi, sine theta, cosine phi, sine theta, sine phi, and cosine theta. Okay. So we can write everything down. The p t prime d omega just equals to this one. Just write it down. Write it down. And after solid integrate over the old angle, we find this one. The pt prime d omega equals 2 over 3 e squared c to the c cubed v dot, the same, and gamma to the fourth, okay, gamma to the fourth. So this one agree with 14.31, and or you can, if you don't like this one, you can write into 14.47 in terms of P change rate. So when beta close to 1, the P T prime over the omega is here. Or you can write into this form. Just rewrite into here. Beta close 1. Okay? Beta close 1. We can rewrite into this form. Beta close 1. Beta cosine theta. Gamma will be very, very large. Okay, rewrite everything. And we rewrite this one into this one. So you can practice by yourself, or you can consider this one here and here, this one and this one as an extra bonus. Write your answer to me. Okay? And from this equation, we know one sense, theta maxima will be close to 0. That will be maxima here. Okay? Angle of maximum intensity, and chi-square, square root of chi-square, 1 over gamma. Narrow cone like a searchlight because gamma is very large. For the synchrotron radiation, gamma will be 26,000. Okay, so angle will be focused. It's just a very narrow searchlight, unlike the previous case. Unlike the previous case. So radiation energy will be focused here, very small and focused, cone-like searchlight. Okay, so we will use parallel to the velocity to accelerate the particle, and we will use perpendicular force to uh, radiate to generate radiations. So in other words, if we want to generate this case, we will use electric field. Electric field is parallel to the particle motions. And for this one, how to bend the particle, how to adjust, that we can use magnetic field. Let's dipole magnet. Dipole magnet can be used to generate radiation. Electric field can be used to Electric field inside a cavity can be used to accelerate a particle. So case 1 is acceleration. Case 2 is decelerations. Gain energy, loss energy. Okay, maybe I should stop here. One more. The final exam will end here. The final exam covers Chapter 10, Chapter 11, and Chapter 14.1 to 14.3. That's it. That's the end. Chapter, we still have two classes. Two classes, but not included in the final exam. We just consider as giving you more information about synchrotron radiations. For example, here, synchrotron radiations. Okay, I will give you the knowledge of synchrotron radiations and how to generate high energy, that's undulator and wiggler, for synchrotron radiations. The end. Okay, so I will stop here. See you next time.